Hello, very good morning to you all, and thank you for joining us here at day 2 of UPEC 2021. Again, we are proud to support and participate in this event, especially as Teesside University is a long-time partner of ours. So again, today we'll be sharing some information on a very interesting project from the University of Duisburg-Essen that we are supporting. The Nextgrid project aims to look at the challenges facing the next generation of power grids that will contain a higher percentage of renewable energy sources. My name is Daniel Brown. I'm the manager of the Lucas-Nuelle Academy, and also with me here today we have Professor Hendrik Venegeerts from the University of Duisburg-Essen, Marc Woestefeld, PhD student at the university and the person responsible for the Nextgrid project. And with me here we have Fabian Schwarz, the product manager for power engineering here at Lucas-Nuelle. In today's webinar, we want to highlight the collaboration between the University of Duisburg-Essen and Lucas-Nuelle to achieve the stated goals of Nextgrid. For this project, Lucas-Nuelle has adapted its projects to better suit the research purposes, which has been critical to help to achieve the main objectives of this collaboration, which is to explore the control and operation strategies of the next generation of power grids based on purely renewable energy sources. The challenges posed by next generation grids need to be studied and understood, and of course, appropriate solutions to these challenges need to be explored. The team at the university have been able to achieve the simulation and emulation of future energy systems and the grid forming control by combining the products of two companies, Lucas-Nuelle and OpalRT, and implement them for the investigation and research purposes. We've prepared a short video which will explain this collaboration in more detail and will give you a better idea of how this project has been implemented. And as we have the experts involved in this project here with us today, we'd like to offer you the chance to ask any questions that you might have about the project at the conclusion of the video. So please just write any questions that you might have in the chat and we'll address these when we come back. So we'll take a look at the video now. And if you have any questions, please just write them in the chat, either in Zoom or in Hoover. We're looking at both of the platforms. Can be a little bit confusing at times, but we're covering both of those. So if you have any questions, please let us know and we'll join you when we come back in about 20 minutes.
Hi, my name is Marc and I'm a research assistant in the Institute of Electrical Energy Systems at University Duisburg-Essen. Today, we want to show you how we are using Lucas-Nuelle equipment in our research project Nextgrid. For this, we will show you how our actual laboratory setup looks like, how it is related to our Nextgrid project, and showing you some results of our grid forming control on Lucas-Nuelle hardware, besides some background information.
Welcome to the lab at Duisburg University. I would like to give you an overview about the Lucas-Nuelle training systems. Many similar projects have proved that our training solutions can be used in research topics. We designed them to be a realistic replica of the power engineering systems. To achieve this, we include many industrial components. The devices in the training systems are modular and flexible to use. Every training station can be used independently, but in a smart grid, they can all interoperate intelligently. Institutions that perform training and research at the same time get the most benefits from the systems. Let's start with our tour through the lab. We find first a prototype of a wind turbine with a synchronous generator. Since our standard hardware is designed for another type of generator, we have customized it according to the requirements of the University of Duisburg to work with a permanently excited synchronous generator. The firmware for the controller of this special equipment has been developed in cooperation with the university. Lucas-Nuelle is very interested in bringing this product to the market very soon. Let's move to the training setup for high voltage direct current transmission lines. This system consists of two converter stations with IGBTs and a bipolar setup. It is used, for example, to learn how to couple two different power grids with the different frequencies and voltage levels. The systems allow the emulation of a short or long distance connection replicating the most common application of transmissions over long distances to reduce losses and other unwanted effects. Another important feature is the operation as a STATCOM facility for reactive power control. In Europe, there are many offshore wind turbines connected to the mainland using this technology. Combining the high voltage DC transmission setup with other training systems, a realistic emulation of complex projects in the laboratory is practicable. For example, in the recent days, we have recreated a very interesting project where the high voltage DC transmission concept is used. Integrating the training system for wind turbine and pump storage, it was possible to replicate a downscaled version of the NorthLink project using a special SCADA interface. The NorthLink is a green connection of German and Norwegian electricity markets by means of high voltage direct current transmission cable. This proves that student projects, master theses and research activities can be realized. More information about it can be found in the video description. Here we find the training system for synchronous generators. Fundamental topics like manual and automatic synchronization and protection can be covered, but also more advanced application can be performed with the same setup. The behavior of different types of conventional power plants like gas turbine, hydroelectric, coal-fired or nuclear power plants can be realistically emulated. Additionally, the same equipment can be used to investigate a microgrid. Here, the main generator sets the parameters to form the grid in island operation, and then the effects on frequency and voltage can be observed when connecting loads or other generators. Different controlling techniques, like droop control, are used here to stabilize the system and reduce fluctuations. Moving to the right, we find our double busbar training system. It can be used to study the fundamentals of power distribution and switching techniques for changing busbar operations without interruption of the power flow. More advanced experiments such as grid control methods and energy management can be realized by interconnecting the training systems via double busbar to form a smart grid or microgrid. For that reason, this system is considered the control center of the whole power engineering laboratory. Next, we have a three-phase photovoltaic system with grid-connected inverter and battery storage. This combination has become not only very popular in Europe houses, but also in the industry. This training system allows the student to investigate many topics on photovoltaic, starting with fundamentals like maximum power point tracker, shading effects, and provision of reactive power. Later, students can learn about more complex topics like voltage regulation with a local network transformer, energy management, and operating reserve of a household by means of a battery storage. Next to the photovoltaic system, we find the standard setup for wind turbines, including a double-fed induction generator, which is commonly used in real applications. This system emulates the characteristic of a Vestas V80 wind turbine and provides a wide range of related topics like physical principles of aerodynamic, synchronization of a generator with the grid, and regulation methods such as active and reactive power control and pitch control. The experiments can also be performed in the absence of wind inside the laboratory, thereby ensuring a safe environment for the students. Like I have mentioned before, the wind power plant can be combined with a high voltage DC transmission line to study further operation modes. Since the understanding of basic concepts of power electronics is very important, we introduce here this training system with a self-commutated power inverter with IGBTs. Many basic experiments can be performed, such as analysis of different types of modulation and their harmonics, 1- and 4-quadrant operation, and operation as a single or three-phase inverter. If we combine the inverter with an asynchronous motor, further experiments can be implemented. Now, for research purposes, we have included a MATLAB interface to reprogram the inverter and be able to test different models which can be designed with MATLAB Simulink. To complete the smart grid laboratory, energy consumers must of course be integrated. For this purpose, we have here the energy management system. A variety of static loads can be used to emulate different consumers in the electrical grid. Using this controller, we can also learn how to perform automatic reactive power compensation with capacitor battery like it's commonly used in the industry. This completes the Lucas-Nuelle equipment of a power engineering lab here at the University of Duisburg. Now I would like to take a closer look to the PV system to show other important features. Along with all our systems, we will find interactive courses that can be installed on a computer. The multimedia platform used here is called LabSoft, and it consists of theory background, animations and wiring circuit diagrams, practical exercises, and real-time evaluation. Additionally, each course has different virtual instruments that will make the configuration of devices and data acquisition easier. Using different SCADA interfaces, our training systems can be controlled and supervised. In the example here, the common combination of photovoltaic system and battery storage is set up. The house supply is regulated by the battery storage in normal operation. In manual control mode, the battery storage can be charged or discharged by adjusting the power set point with a slider. First, the charging is set to 750 watts. The energy flow can now be observed in the SCADA interface. Let's change it here to discharge. And check now this energy flow change. On the inverter side, we observe the slider controller for the D-rating. According to the country-specified regulations for renewable energy sources, power reduction should be available for reducing active power in order to avoid network overload. Finally, we conclude our tour with the Opel RT amplifier. This 4-quadrant amplifier allows the development of innovative grid-forming control and operating management concepts. Power grid models created in any real-time simulation environment can be tested using the Lucas-Nuelle equipment and the Opel RT amplifier. This combination provides a complete solution for investigating the various challenges of a modern smart grid. This was just an overview of the lab and the training systems. We will continue here with the presentation of Marc Woestefeld. I look forward to receive your comments and questions at the end of the webinar. Thanks for your attention.
We are using Lucas-Nuelle because of its easy and convenient use and safe operation. We can use the equipment for both cases, research and education. Since Lucas-Nuelle offers a broad variety of products, there is also the possibility to represent a lot of grid assets. Additionally, there is a strong cooperation between Lucas-Nuelle and the University of Duisburg-Essen. In combination with the programming via MATLAB Simulink, this enables easy modeling and modification for a prototype controller. Besides this, we are able to develop even more application and equipment together. Last but not least, we can contribute to the educational content with state-of-the-art research content. For the connection between our research project Nextgrid and the used equipment, I would like to pass over to Professor Venegeerts.
My name is Hendrik Venegeerts. I'm head of the Department of Electrical Power Systems of University Duisburg-Essen. And in this role, I'm also leading the research project on Nextgrid, or Next Generation Grid, where we are working with the equipment of Lucas-Nuelle and Opel RT in our field laboratory. And in order to motivate why we are using this equipment in our lab, I want to describe briefly what is the background of our research project Nextgrid. We have ongoing developments in the electrical power systems, not only in Germany, all over the world, but some issues are also accelerated actually in Germany. One of them is the high transmission capacity needs due to the regional concentration of renewable power plants like PV or wind power in feed. This leads to really high transmission needs and therefore to the need of network reinforcement. However, network reinforcement actually, the speed of network reinforcement is not coping with the speed of the development of the energy transition. And therefore, we have a complex system operation as well as system stability monitoring, since there are systematic congestions in the network which has to be managed somehow. Moreover, due to the high different power flow situations in the network, we need both a lot of static but also dynamic reactive power sources in the network. This can be solved by new system stabilizing components on the one hand, and on the other hand, also by enhanced system operation strategies, which really have to come from a system point of view, not just from local control attitude. Another ongoing development is the phase out of conventional power plants. Next year, the last nuclear power plants will be phased out, but also at latest until 2038, all coal-fired power plants will be phased out in Germany. This means we have less synchronous generators which are operating in system. In principle, only hydropower is left and gas-fired power stations. And in contrast, the renewable generation usually is converter-based. So there's a different technical interface to the network. However, the actual network is mainly designed or based on the existence of synchronous generators with some of their special characteristics. Of course, based on their power synchronization behavior, but also on the mechanical inertia they are providing and on the instantaneous provision of reactive power and current if anything in the network changes, and according to their stabilizing effect they have on the network. And the main solution, which is desired for the future, is to make the converter grid forming, not just grid following like the most converters today are. And our Nextgrid project is aiming at both on the development of new converter controls, which are grid forming on the one hand, and on the other hand, to include them in an overall system-related control and system operation method. Therefore, our project Nextgrid aims at this grid forming control and the control strategies, both of them, and we are really aiming at a system of the future where we have 100% renewable generation as our vision. We have to develop possible future grid situations and modes, of course. Yeah, of course, you can expect what is coming during the next decades, but we have to make a best guess about what is going on. We have to develop novel control schemes for the system operation, but also for the grid forming converter control. We have to analyze protection and information of communication needs which are in the system and really to test them. And we have to validate the concepts in this power hardware in the loop fill laboratory using Lucas-Nuelle equipment and Opal RT real-time simulator and amplifier. To illustrate this laboratory, first of all, just by a rough overview, showing the main components here. On the right-hand side, we have our downsize but close to reality equipment of Lucas-Nuelle, where we have the option to utilize our own inverter controls. Since we are not able to build the whole European network here in a nutshell in our laboratory, on the other hand, we need the real-time simulator to have a dynamic simulation of the surrounding network. In between, of course, we need a 4-quadrant power amplifier. This enables us to test the controls of close to reality environment. Of course, you could say we could simulate everything, including all of the grid forming controls, and that is what we are doing in development as well. However, we see a great benefit in doing this in the laboratory as well, since then automatically we will be faced with natural inaccuracies of measurement and communication latencies, which are taken into account and which in the end give more reliability and trust to our results. Also, this allows for fast prototyping of controls and the test of interaction amongst them. Moreover, as an overlay, we also have a wide area monitoring system, a supervisory control, enhanced with a dynamic security assessment system, DSA, which like it is used by transmission network operators already today, and where we can test whether our controls which we have development will also be a cope with today supervision concept and methods, or whether there is need for new algorithms to supervise the system.
Thanks for the explanation. Now for some lightweight theoretical background. In principle, there are three different forms of control strategies: grid forming control, grid following control, and grid supporting control. Supporting will not be mentioned here since we are focusing on grid forming. But in general, grid supporting can be arranged in between the other two methods. Actual inverter-fed distributed energy resources are grid following controlled. Upcoming generation could be grid forming controlled. To be mentioned, not all inverters have to be grid forming controlled, as long as the main properties of the grid will be maintained. Grid following means it measures the actual grid angle and adjusts its output voltage to achieve the reference currents. So, as the name says, it follows the grid. With other words, it will act like a current source. Grid forming control has to have a self-contained rotating voltage source which will just synchronize to the actual grid situation. There are two main requirements for the grid forming control scheme. First, it should behave like an ideal voltage source with an internal impedance. Second, it should have an inherent response to changes in the grid. So, it provides the highly required inertia while substituting synchronous generators with inverter-fed energy sources. Mechanically, this would mean that there is a mass attached to the rotating output voltage vector of the inverter, which is connected to the grid voltage source through a spring damper system. This will provide a swinging synchronization and damped behavior mimicking a rotating mass. Therefore, it should act like a real synchronous generator. Nevertheless, it could overcome some issues of the synchronous generator, which could provide best of both worlds. Now, we will look at the behavior of a grid forming control. First set, the difference to a grid following control is just visible in the first few grid periods or in total absence of a synchronous generator. You are less likely to run an only PLL-based system, which is somehow normal for the grid following controls in an islanded operation. Without additional control techniques, the grid frequency will drift apart. The main difference between both control methods will be visible after the PLL found the grid angle. The grid following control will provide its referenced currents. The grid forming control will swing around the operation point and providing supporting currents. Clearly, grid following control could be tuned in such a way that it will behave somehow the same after a few grid periods. But with total absence of synchronous generator, it will easily drift away. When the contingency happens, or at a simple grid impedance or angle change, the grid forming control will react a little inert to provide the emulated mass. Due to the synchronizing behavior, it will change its output angle, and because of the damping, it will become stable. Regarding the current, we can see the difference between the ideal following converter and a grid forming controller. At the moment the contingency happens, there is an angular mismatch at both controller types. Grid following control will find the angle very fast and adjust its output voltage. Grid forming control will slowly synchronize. Hereby, it will provide some active and reactive power to stabilize or at least support the grid. When looking directly at the output power, it is visible that there will be additional energy transferred from or to the grid due to an intentional angular mismatch. Grid following control will just show small derivations from its previous set point, since it will follow the grid. So, grid forming control will incite this power flow to mimic an inertial response of virtual rotational masses. Let's move on to the demonstration. What I want to show you now is a fault right-through test of our developed grid forming control prototype. So we want to have an voltage drop or angular step. For this purpose, we could use the Lucas-Nuelle fault box, but it is coupled to an almost infinite bus in regard to our lab equipment. To have a frequency variable system, we will use our real-time simulator in addition to a power hardware in the loop amplifier. Here you can see that even connection from the Lucas-Nuelle system to other lab hardware is possible. We will use a high voltage transmission model based on the respective Segre benchmark grid and resubstitute the Synchronous generator on bus 12 with our power hardware in the loop wind farm. For the fault, we add a 3-phase short circuit on bus 5. Let's go! Let me show you the results. In the upper left corner, you can see the voltage. In the upper right, the reactive power. In the lower right, the active power. In the lower left, the frequency. In the voltage, we can see the specific voltage profile of the fault right through test with some additional transients after clearing the fault in all plots. The frequency will rise due to the fact that some loads were decoupled so that there is a power mismatch at the Synchronous generator. The well-known reactive power behavior is visible to support the voltage recovery. In the graph for active power, the reduction due to the voltage drop is observable. In other cases, there could be other priorities except reactive power. After fault clearing, the power is rising to synchronize itself with the grid. This behavior can be explained with the power mismatch between nearly constant infeed on DC side and the reduced outgoing power. The virtual rotating mass would be accelerated. Since the virtual mass is configured to be low compared to the synchronous generator, it will accelerate faster than the other synchronous generator. Therefore, it has to decelerate for synchronizing. To conclude this short demonstration, we are able to combine both education and research with the equipment of Lucas-Nuelle in our research project Nextgrid. Due to the expansion capabilities and modularity, there is no limitation for using only Lucas-Nuelle equipment, which will provide more flexibility. Additionally, we saw that the grid-forming controller could provide some behavior like the synchronous generator. Therefore, it could help to stabilize the grid in the future. Thank you for your attention and attendance. I'm looking forward to your questions and comments. Now let's move on to the Q&A session.
Okay, we're back after the video, so let us know if you've got any questions regarding the video that we had. We have the experts here again. So we've got a couple of questions have come in on Zoom, so I'll have a look at those soon. But first, I might just ask a few questions to the panelist here. So Professor Venegeerts, maybe you could just give us a little bit of an idea or a rundown on developing the path for a grid forming converter control. Is there anything that you can say about that and what you've discovered?
If you look at conference programs, not just from UPEC conference, but all from others, you see an exploding number of contributions about grid forming control with a lot of control strategies. So there's a lot of research, which on the other hand also means there is no standard until now. Otherwise, research would not be necessary anymore. If you look at grid codes, you see that there still is no detailed definition of what grid forming in detail means. And as a consequence, there is no detailed specification for grid forming control as we already know for other renewable energy sources or or generators as well. If you look for the Europe case, according to the European regulation, until July 2025, the existing EU connection codes have to be revised. So there's a possibility and also the need to enhance those specifications on a European level for grid forming control. And there's a recommendation that all of the research findings until now and maybe even beyond that can be included in this specification. As regards the time horizon, you already see that there's at least a time span up to 4 years until 2025. And until all of the products have been developed and put into operation, we have to assume that there will be another time frame of a few years. So until we see those equipment into the networks, it might be a time horizon of at least 4, maybe 8 years. And then there will be no special high penetration, because this needs some time until the equipment comes into the network. So classical solutions that are already technically available will also play a role during the energy transition. However, at least in Germany, and I think also in other countries, it is investigated whether existing primary equipment, that means existing converter architecture, can be enhanced just by other controls to be grid forming. A special interest is paid to STATCOMs in this case. And this could be a way to get them faster into the network than by installing new equipment.
Okay, well, certainly very interesting, and shows you the value of research like this to really understand and give us some strategies going forward. So thank you for that. Marc, as we know that there is many different types of control strategies, perhaps you could just give us an idea, a little bit more of a rundown on the virtual synchronous machines and generators, what your findings are and how you're working on that.
Yeah, for sure. So as you say, there are some grid forming control strategies, and we are working with a direct voltage control, which is based on the here developed control structure. And this is somehow a decoupled control strategy, because we think these control strategies could provide some advantages, like decoupled active and reactive power controls. These decoupled control strategies also overcome some main difficulties in grid forming control strategies, like the current limitation, which could be handled in our control strategy somehow. Formerly, it was a partial grid forming behavior, but now we could develop it even further, and now it is fully grid forming control. And our main goal here in this control strategy is that, in contrast to virtual synchronous machines or something like that, that this is a multifunctional applicable control, that you can apply it on certain voltage levels or grid topologies without any large parameter changes, and it should still show a deterministic and adjustable grid forming behavior, since we heard that not all participants have to have grid forming behavior. It could be somehow turned off, or some could play a role there.
Okay, thank you very much. Okay, Fabian, we also seen in the video you've developed some new products, especially for this lab. Maybe just give us some idea about hardware development. So in this case, we've seen a need for this new type of product. Maybe you could just tell us what is it like with hardware development here at Lucas-Nuelle? Is it a long process, or?
Yes, it's depending on which system is needed from a customer side. So we have a lot of requests about inverters that can be programmed with MATLAB, like PV inverters for MPP trackers, to design them, test them. And we would like to provide hardware that is safe to use, so the students cannot destroy anything. And for this development, we need support like this cooperation with the University of Duisburg-Essen to to develop such a system, and take a lot of time. This project, I think with inverter 2 years, so in the middle of the next year we have maybe a prototype and can start with marketing and so on.
Okay, and in case you didn't know, all of the development also gets done here in-house. We have our development engineers, people such as yourself that will develop the idea working together with our engineers here, and then everything, prototypes, everything will get built here, and then further developed. Software gets written, hardware gets developed, things like that.
Yes, so we are designing the hardware and make changes that fits to the need for the university, send them, they test the software, and yes, say what can we do better in the future. And yes, so in the future we will design a special hardware for this application, but this takes time and a lot of prototypes.
It does, yeah. This actually fits into a question that's just come through from Neville from Teesside. Teesside, of course, is a great partner of ours in the UK. Neville asks, are there any new products that LN could recommend that would complement the laboratory that we have at Teesside? We have machines, transmission, distribution, renewables, equipment in use at the present. Do they have this new product? Probably not if it's brand new. Maybe
no, so I guess they have a lot of equipment. I was there for training, but not in detail. I guess they have the state-of-the-art training systems at the moment, but in the future there are coming a lot of new things, and then we have to look if it's matched to the curriculum and to their students. Okay,
perfect. Okay, another question that's come through. Are there LN instruments to measure the rate of change of frequency, which could be used when moving in and out of island mode?
Yeah, we have some industrial devices, but they are a little slower. But the best way is to use our machine test system. With that machine test system, we can measure the speed of a generator and can log the frequency and the speed of the machine in our SCADA software, and visualize the frequency changes. So not also the island mode and grid parallel mode, also if you connect another type of generation or a consumer, you can see directly frequency changes and visualize that and measure it with the SCADA logger.
Okay. So we'll just do a quick look. Professor, did you have something to add there? Or?
Yeah, I just wanted to add that I think, and Mr. Woestefeld also stressed this in his video, the strength of a laboratory together with Lucas-Nuelle is that we are also able to include other equipment as well. It's not just to replace Lucas-Nuelle equipment, but to make it the whole system even more close to practice. So, for example, in our laboratory, we are using PMU, like is done in the network, to include them in the SCADA system. Mr. Woestefeld want to add something to that.
Of course, there are the possibilities to extend our equipment. We have a lot of customers, they bring their own devices from other manufacturer we are not offering, and combine this system like PMUs, could be Siemens or Schweizer relays. We have,
I think that's the advantage of using industrial components and integrating those into the learning methods so that it is interchangeable with real world and other industrial components, because everything is real. It's not simulated as, it is actually following real world characteristics and equipment.
It's downsized real systems, and we are learning from our customers if they do something like using other devices from other manufacturers and replicate a real scenario, and we are learning from that and integrated it in our portfolio if it's matching to other customers too.
Yep. And I think that's important to also stress that on this project here, we're basically talking about research and on an important topic, but we can also use our equipment for learning as well. So going from the fundamentals right through to bringing it up to the point where we can implement research.
There's a question.
Okay, Marc, would you like to add to that at all?
Yes, maybe just for example, we recently added in our lab this PMU from Siemens here. And as I said in the video, with this Lucas-Nuelle system, you can easily add those components on your own when they are not available of Lucas-Nuelle. And for example, this is a protection relay, a distance protection relay from Siemens with this PMU feature we want to include in our research too.
Okay, great. Okay, does anyone have anything else to add to that? Looks like there's no more questions that have come through, so... Oh, one question's just come through. Is Ellen seeing any product shifts across different countries? So I'm not sure if that's me asking if there is, do you have are you selling different products in some countries as opposed to other? I guess in Europe, we might see a lot more of wind power as opposed to solar power in some countries, or maybe you have some different insight into that.
So we are selling all our products around the world. For some different grids, we have to adjust the hardware. So if you have a grid in the US, so it must be the frequency and voltage we have to adjust, but around the world we have the same products. And did I understand the question right? I don't
Maybe know. If you just let us a bit more information, but we're on our last 2 minutes before we get cut off. So just got a statement from Teesside Uni here. So thanks, Professor. We currently have a Master of Science student who has incorporated Alstom relays for line protection, and it definitely adds real world value. So great. Bit of inter-university information there, always great to see. Okay, so I think that's all for today. I want to thank everyone who's joined us again. Again, unfortunately, we had someone ask if it's the same video as yesterday. It is. We decided to go with the same video throughout here, but we're always there to ask questions. But again, thank you for your time. Professor, Marc, Fabian, thank you again for joining us. And we wish you all a great day and enjoy the rest of the conference. Thank you.
Have a great day.
Have a great day. Bye-bye.